Hey, hello everyone. Welcome to the discussion of weekly contest 488 of LeetCode. We will be discussing all the problems A, B, C, and D. So let's start with the very first problem, which is count dominant indices. So we are given an integer array nums of length n. An element I is called dominant if num set I is greater than average from nums at I plus 1. That is the suffix of that particular index. Uh, let's say we are considering this particular index, then this particular value, the index value should be greater than average of its suffix excluding that number itself. For this 5, these two numbers appearing after it, 4 and 3, will be considered. For this 4, the number appearing after it, 3, will be considered, and so on. So for an index I, its suffix will be considered, excluding itself. And that particular value at a particular index should be greater than average of its suffix. Now, our task is to count the number of indices I that are dominant. The average of a set of number is obtained by adding all the numbers together and dividing the sum of total numbers of number. Note the rightmost element of an array is not dominant because there is no suffix for it, right? Okay. So seeing the constraint of this problem, it is the value of n, that is the length of array, is 100, and the value of elements present in it is also 100. So if we pick up an index and calculate the sum of its suffix and then calculate its average, it will be like we need a loop to go for each element and another loop to calculate the sum of its suffix. So it is n square, and it must pass in this given constraint. But can we try to optimize it? For example, let's say we have this particular test case. Here, if we have sum from uh, index 2 to 3, let's have an indexing first. This is one based indexing, and the first element is index 1, second element is index 2, third element is index 3. All right. Now let's say we want to calculate if index 2 is dominant or not. So we have the element at index 2, which is equal to 4. Now we want uh, this particular value, average of its suffix. So what is the sum of its suffix? It is equal to 3, and number of elements, it is equal to 1. So let's term this as suffix sum, suffix average. All right. So this is equal to 3. Now since 4 is greater than 3, this particular element is dominant. Note that this sign represents strictly greater than, and 4 is strictly greater than 3. So this is a dominant index. So one of the computations we required was to calculate the suffix sum, and it leads to a O of n complexity. Currently, all right. Can we reduce it? Let's say if we have suffix from sum for index 2, which is sum from index 3 to 3. All right, closed bracket. Now suffix sum for index 2 is equal to sum of indices 2 to 3. Okay, so if we have, okay, index 1 is equal to sum of indices 1, sorry, 2 and 3. Okay, all right. If we have suffix sum for index 2, can we calculate suffix sum for index 1? Yes, we can say suffix sum for index 1 is equal to suffix sum for index 2 plus value at index 2, isn't it? All right. So if we have suffix sum for index 2, we can calculate the suffix sum for index 1. Uh, if we generalize this, we can calculate suffix sum of index I if we have suffix sum for index I plus 1. And what is the base case? Suffix at I is equal to suffix at I plus 1 plus array at I. Okay, we have just generalized it. What is the base case? Base case is suffix at index n is equal to 0. All right, because that particular element itself is not included. All right, here it is I plus 1. So we can just implement this thing to calculate suffix sum, and we can get rid of this O of n complexity. So overall, what do we do? Go to each index, calculate its suffix sum using this particular formula. Now for a suffix sum, calculate the average by dividing with the number of elements we have in suffix. Now, if the value at that particular index is greater than the average suffix, then it is a dominant index, else it is not a dominant index. One more thing, if we have such a calculation, that is a by b is greater than or smaller than c by d, and we need to do double calculations for this. We want precision. All right, we don't want this values to be rounded off. We want if the decimal values of a divided by b is greater than decimal value of c divided by d. We want precision. So we can replace this particular thing with such expression. uh, if you have completed your course of COA, then you might be aware that decimal computations may lead to wrong values sometimes because of the way double and long double are stored inside the computers or registers. So that is why division is not generally preferred in decimal form. So just convert this in the form of multiplication. This division of D is moved to LHS and this division of B is moved to RHS, and this expression is obtained. So every time when you need this expression, convert to this particular expression and just implement it. So let's move to the implementation. Initially, base case, sum is equal to 0. The count represents the number of elements in the suffix, which is 0 currently, and answer represent number of not dominant indices noticed so far. Now start with the last element and move up till the first element. Now if, okay, let's understand this thing. If the current value is greater than average is sum divided by number of elements. Now this expression is same as this expression, a by b is greater than c by d. So how can we replace it? We can replace, here division with 1 was there, multiply it with RHS. Here division with CT was there, multiply it with LHS. So same expression, just better computations. Now, if this expression holds, this is the dominant index, increment the answer counter by 1. At the end, we have visited one more element, so increment counter by 1. And we had generalized form of suffix sum, which is uh, suffix sum is equal to current suffix sum plus the current element. And this is updated like this, and we have got our answer. So what is the overall time complexity and space complexity of this code? The time complexity is O of n initially, necessarily, because we are iterating over the whole array just once. What is the space complexity? Are we storing some extra array or something? No, we are just having an initially predefined vector which we are given in input, so it is not taking any extra space. So the extra spaces taken by us is O of 1. If we had implemented the same suffix something, then we might be having a suffix sum array, but we have reduced that complexity as well by using a variable instead of a array for suffix sum. So overall time complexity is O of n, space complexity is O of 1. So that is it for the first problem. Let's move to the second problem. Okay. The next problem is merge adjacent equal elements. So we are given an integer array nums. We must repeatedly apply the following merge operation until no more changes can be made. If and two adjacent elements are equal, if any two adjacent elements are equal, choose the leftmost such adjacent pair in the current array and replace them with a single element equal to their sum. After each merge operation, the size of array decreases by 1. Repeat this process on the updated array until no more changes can be made. Return the final array after all possible merge operations are done. Okay, notice this particular thing, that always the leftmost adjacent pairs are removed. All right. Now let's dry run some of the test cases we have. For example, this test case. Here, what is the first leftmost matching pair? It is these two pairs, index 2 and 3. Index 2 and 3 are both equal to 1. So replace it with their sum, which is equal to 2. Now index 2 and 3 again. This particular 2 is transferred here and these two ones are transferred here. Let me highlight this. These two ones move here and this 2 moves here. All right. I don't think there's need of indexing here now. Now in this array, these two values are equal, so they will be replaced with their sum. And the final array, which is 3, 4, has no matching values. All right. So this gives us the final answer, which is 3, 4. Now another test case, which is 2, 2, 4. What is the leftmost matching pair? It is 2 and 2. It gives 4 value. These two are the leftmost matching pair. So it gives us 4. Another 4 present gives 4 again. All right. Now these two 4s are matching again. So they give 8 as the output. So the final array, which is 8, is returned. All right. Now in this test case, is there a matching pair? No, 3 and 7 are not equal. 7 and 5 are not equal. So there will be no operation performed. And this is our final answer. What do we analyze from it? The test cases are too small for having good analysis. So let's build some good test case. For example, here we have 4, or let's say 8, 4, 2, 2. 8, 4, 2, 1, 1. All right, this is good. Now, what is the leftmost matching pair? It is equal to 1, comma 1. Okay, so let's start from the beginning. Is this pair matching? No, it is not. Is this pair matching? No, it is not. Is this pair matching? No, it is not. Is this pair matching? Yes, it is. So let's highlight it. This pair is matching. All right. So how will it be replaced? 8, 4, 2, 2. Now, is there any matching pair? Start from the leftmost one. Is this pair matching? No. Is this pair matching? No. Is this pair matching? Yes. Highlight it again. Apply operation, which is 8, 4, 4. Now start from left. Is this pair matching? No. Is this pair matching? Yes. So replace it with its sum, which is 8 comma 8. Now is the leftmost pair matching? Yes, the first pair is matching itself. So it is replaced with 16. All right. So what are some of the observations which we get from here? One of the observation is that every time the rightmost element of the array becomes the first matching pair. All right. In this particular test case. So let's try to digest this thing. If up till index I no matching pair is found, the first leftmost matching pair that can be found in future is index I. Okay. Okay. What do it mean? It mean that if we have processed up till index I, if we have processed up till index I, let's say here index 4, then we need not reiterate from index 1 to index 3. All right. Because there is no changes done from index 1 to 3 if we apply a operation after it. And can we apply a operation before it? We have already said that there is no matching pair up till index I. So we cannot perform an operation in this part. All right. If we had performed an operation somehow which leads to index I, then it must be performed with index I plus 1. All right. A operation on this index cannot be performed with its prefixes. It can only be performed with uh, its suffix. All right. If somehow a operation is performed here, which element has the only probability of being a member of matching pair? Can this be a part? No, because changes are done in this part of the array, and this part has already been said as part with no matching pair. So it can never be a matching member of matching pair. All right. Can this be a part? Its immediate neighbor is 2, which is also said that it is not a matching pair. So it cannot be harmed as well. Now for 2, its immediate neighbor, index I, can be changed. And if it is changed as such that its value is equal to 2, as it has happened here, then 2 becomes a new matching pair. All right. So this gives us idea that considering suffixes of the processed array is a good option. What do it mean? If we have processed up till index I, then only check for index I and I minus 1 in future operation. Why? Because if we were doing a brute force thing like we were earlier doing, that is, we first iterated from 8 up till 1 until we found a matching pair. Then when we found a matching pair, we started from left of the array again. 8 and 4 were not matching pair, 4 and 2 were not matching pair, and then we found that 2 and 2 are matching pair. Instead of iterating from left up till this particular index, that is if we had not checked this 8 and 4, because it is very much obvious because this part is not changed, so it cannot be a matching pair. All right. And if we had not checked this 4 and 2, then we must have saved some of the computations. And if we had only considered this particular 2, then in only one step, okay, neglecting pairs from 1 to 3, index 1 to index 3 saves computation. Here the array was very small, it is of size 5. Then also we are saving 3 operations. Let's assume the array was of size 1e5, then approximately 1e5 operations are saved. So this pretty much reduces our complexity from O of n square, that is at each operation finding the first leftmost matching pair, to O of n, that is if we found a matching pair here, consider only the ending index, not the whole prefix of the array. All right. So what is our major idea here? If we have processed up till index I, then only check for index I and I minus 1 in future operations. All right. And if this I and I minus 1 are equal, then check for I minus 1 and I minus 2 as well. And this goes on. Now, keep this in mind. If one element is removed, it never adds upon in complexity in future operation. All right. So using these observations, let's try to have an implementation where in O of 1, we can calculate all the matching pairs, all the valid operations. What do we want to do? Initially, at the first time, we calculate the first leftmost matching pair. Then using that itself, we are finding the next matching pair. All right. So if we have already iterated up till index I, then the matching pair from index 1 to index I, that is up till in the prefix of index I. For example, if we have already iterated from index 1 to index 3, that is 8, 4 and 2, then we want that after finding a matching pair, we need not iterate over these portion again. All right, because it would add upon to our complexity. We can iterate to the right of it if we do not find a matching pair then, but if we already have moved to a index I, then we need not process the left portion completely. So let's see some implementation which gives us some idea. For example, we have a answer array which is the final value of our array after applying all the operations. Now this index I represents up till which index have we processed. If we have processed until index I, then all the elements present before it becomes the part of prefix and they cannot be iterated completely now. Now, if we have moved to an index I, then push that inside our array. Now, if it is a matching pair with its previous element, for example, here, then uh, the last element is answer at uh, last element, and the second last element is answer at second last element. All right. Now, if these two are equal, then they will be replaced with their sum. All right. Now, what is a possible contender in the prefix part? The possible contender is index I minus 1 and I minus 2. All right. Here n minus 1 and n minus 2 were there. So new contenders are n minus 2 and n minus 3. Since the size of array is already reduced, the elements are already as such that they becomes the last element and second last element. All right. Now this particular operation continues until we keep on finding matching pairs. Now since this prefix can be iterated only one time, how? Let's try to understand the time complexity in this case. Here in this loop, in this portion of the loop, we are iterating each element only once. Each element only once. All right. And in this while loop, if we are removing some element, it cannot be processed again. And this does not add upon to our time complexity as we discussed in this portion. All right. If you have already processed until okay, if one element is removed, it never adds upon to the complexity in future operations. So okay, so if one element is removed, it do not add upon the complexity in future operations. If this portion of the code is run, it can be run for a particular index only one time. And if this portion of code is run, it is a O of one operation. All right, break is a O of one operation, so it does not add upon to our complexity. So this particular portion of while loop guarantees that each element is visited only once. And this is a O of one operation. So overall, this while loop, okay, the sum of time complexity of this while loop over this for loop is O of n. All right. How this particular loop also runs once for each element, and this particular loop also runs once for each element. So for each element, it is processed at max 2 times. So for each element, it is processed 2 times. So how many total number of operations that are performed? How many processings are there? Number of elements multiplied by number of times it is processed. So it is equal to O of n into 2, and constant can be removed in O notation. So overall time complexity is O of n. So this is it for the time complexity part. And space complexity. What is the space complexity of this code? We are creating a new array, answer array, whose size can be up till O of n. So this is it. Space complexity is O of n, time complexity is O of n again. So that is it for the second problem. Let's move to the third problem for now. The next problem is count subarray with cost less than or equal to k. So we are given an integer array nums and an integer k. For any subarray, define its cost as the product of the difference between max and minimum element and the length of that subarray. Okay. Uh, Read it carefully. This is the difference of max and minimum element. This is multiplied with length of the subarray, which is r minus n plus 1. Now, return an integer denoting the number of subarrays in nums whose cost is less than or equal to k. Okay. Let's analyze some test cases. For example, this test case. Here, the subarrays are 1, 1, 1, 3, 1, 3, 2, 3, 3, 2, and 2. All right. For this subarray, what is the value of max minus min? It is equal to 0. Max is also 1, min is also 1. So it is 0 multiplied by length, which is 1. It is equal to 0. For this, max minus min is equal to 2. Length is equal to 2. Total value is 4. For this, max minus min is equal to 2. Length is equal to 3. Value is equal to 6. For this, max minus min is equal to 0. Length is 1. So value is 0. For this, max minus min, 3 minus 2 is equal to 1. And length is equal to 2. So total length is equal to 2. For this, max minus min is equal to 0, 2 comma 2. And length is equal to 1. So total value is equal to 0. Now, what do we want? We want the number of subarrays having cost less than or equal to k. What is the value of k? 3. This one is good. 0 is smaller than equal to 4. This one is good. Add dash upon all the good. This one is not good. 6 is not smaller than equal to 4. This is good. This is good. This is good. How many of these subarrays are good? 1, 2, 3, 4, 5. So there are total 5 good subarrays in first test case, which is given in the output. Similarly, for second test case, you can dry run it. Let's move to some of the observations. The first test case is enough to observe these things. So let's move to the observation. Let's say a subarray from L to R. Subarray from L to R is good. All right, what do it mean? It mean that it contains some elements. Let's write all its elements in sorted order. Let's say there were 4 elements: A1, A2, write it in some order: A3, A2, A4, A1. All right, this seems better. Okay, if subarray from L to R is good, and if we write it down in sorted order, let's say A1 is smaller than A2, then A2 is smaller than A3, and A3 is smaller than A4. Then I claim, let's say this subarray is named as P or S. Claim that any subarray of S is also good. This subarray is not of original array, it is of this subarray S. Alright, subarray of a subarray. Alright, is also good. What do good mean? It good mean that the cost is smaller than equal to K. How? Let's analyze this particular set that we have in uh, subarray L to R. For this, max minus min is equal to A4 minus A1. Alright, let's say for some subarray, let's say we are considering subarray from L1 to R. You can take any middle element as well. Okay, if we are considering from L1 to R, A3 is removed. Even if some of the element is removed, what will happen to the value of max minus min? It will always reduce. Why? Because if A1 is removed, then the smallest element increases. It can go to A2. If A4 is removed, the maximum element decreases. It becomes A3. And if the middle elements are removed, no difference is done. All right. There is no difference. The max minus min will be A4 minus A1 as well. So if A3 is removed, max minus min remains same. Decreases or remains same. What about the length? Because we are considering a subarray of L comma R. Subarray always has a length smaller than the original array. Okay. So length also decreases or remains same. What about their sum? We are considering their sum, their product, right? Product of max minus min and length. Since both of these value remain same or decrease, the product of them also. What to remain same or decrease mean? It never increases. And if it does not increases, can it exceed k, value that is decreasing is always smaller than the original value. Okay, and the original value was smaller than equal to k, so the new value will always be smaller than equal to k. The cost of subarrays of S is also good. All right, good means that it is smaller than equal to k. All right, so if for each index L, L, we find the maximum R, which is leading, which gives us subarray L, say AL to R, which is good. What do this maximum mean? Maximum mean that A to L to R is good, but L to R plus 1 is not good. And if L to R is good, L to R minus 1, R minus 2, R minus 3, all will be good because they are subarray of original array. Alright. So if A L to R is good, A L to R minus 1 or A L to R minus 2, everything up till A L to L, all are good. Alright, so if for each such index I, we find the corresponding index R, then we can find the answer. Okay, how? Iterate over all such R's, and for all the subarrays starting from this index, how many good subarrays are there? It is equal to R minus L plus 1. Okay, this is the number of subarrays that can be made starting from a particular index, and the ending point is smaller than or equal to a given point. Number of good sub arrays for this point is R minus L plus 1. All right. Now our all task is to calculate all the good sub arrays starting. Okay. Task is to iterate to each index, calculate all the good sub arrays starting from this point. All right, this is our overall task. So what will be the time complexity of this task? For each starting index, for each index I, we want the ending index. For each I, we want a R. So finding a R is O of n operation, and iterating over each index is again a O of n operation. So overall time complexity is O of n into n. But what is the constraint of n? It is 1e5. So it won't work. We want some new optimizations as well. So one more observation. If for a index I, R is found as J, okay, corresponding R is index J. Okay, let's visualize this thing. here there was a index I, and here there was an index j. Now we say that this part is, or this subarray is good. Now if we increase our index I, let's say we move to index I plus 1, then what can we say about uh, subarray I plus 1 to j? This is I plus 1 up till j. Okay, this particular subarray is also a subarray of, this red subarray is a subarray of green subarray. Okay, if we term this green subarray as S, then this red portion is a subarray of S, and we already concluded that any subarray of S is also a good subarray if S is a good subarray. Okay, so this red portion is also a good subarray. Then the index of, or R for I plus 1 is greater than equal to j. Okay, because this is a good subarray. It's enlargement, that is increasing the R, that is maybe this subarray I plus 1 to j plus 1, it is also good. Maybe j plus 1 to j plus 2 is also good, but j plus 1, sorry, I plus 1 till j plus 3, this is not good. All right, then the corresponding R for this particular I will be equal to j plus 2. Okay, I just mean that corresponding R for this I plus 1, it will always be greater than equal to this J. Okay, so this translates into a classical two-pointer problem. All right, so for each index I, find corresponding J using two pointer, and the answer for all subarrays starting from I is equal to is equal to j minus I plus 1. Okay, so this is it. Let's move to the implementation portion of this problem. So this R represents the uh, ending index for each indices for initial portion of the array. For index 0, index 0 is the R initially. Maybe R increases, which we will do in this portion of the code, but initially we assume that R is equal to 0. Now answer represents the number of valid subarrays, n is the size of our array. We take multiset because the numbers can be repeating. All right, so, and we want the difference between the largest and the smallest elements. So each element has some of its contribution, and if that particular index is removed, the duplicate value should not be removed. So we are using multiset here. So let's move to this portion of the code. In the for loop, we are just iterating over to the starting indices. Now to find the uh, ending index, we will know that ending index only increases, it never decreases. So let's assume the next index is R plus 1. R is a valid subarray. So let's find about R plus 1. Insert it into the set, find the difference between max and min. Now check if it is good. If it is good, then product of max and min and the length is smaller than equal to k. Then this R is valid. Else, this R is not valid. If it is not valid, we have inserted a wrong value inside our set. All right. So erase it from the set. Remember, this is the method of erasing an element from multi-set. All right. And uh, since this element do not leads to a good subarray, so R is one smaller than the current element. So R is not incremented, and we can break because we are sure that if this is not valid, then its super array is also not valid. Okay, no need to move rightwards anymore. Now, initialize answer or increment answer with the number of subarrays starting from index I. It is equal to r minus I plus 1. Now, this array portion, or let's say this array portion is done. Now we want uh, this array portion is done. Now we want the array portion starting from index this. Second, all the arrays starting from index 1 is done. Now we want all the elements starting from index 2. So we need to remove this particular element from our set. All right. So that is what we are doing in this portion of the code. At the end, return answer. Answer is the number of valid subarrays. That is it for the third problem. Let's analyze the time complexity and space complexity of this code. Time complexity, this is a classic uh, two-pointer problem. I and R, both of them do not visit same element twice. All right. In this portion of the code, they can visit, but it is a O of 1 operation, okay, for each index I. R will always increase. It will never uh, decrease. R will remain same or increase. It will never decrease. So each element is visited at most twice in this portion and this portion of the code, including the for and while loop. So this is a classical two-pointer problem with time complexity O of n. What is the space complexity? We are creating a multi-set uh, which can contain up till n elements if the R for first index is n itself. All right. So space complexity is O of n again. So that is it for the third problem. Let's move to the next problem now. So the next problem is maximum score using exactly k pairs. We are given two integer arrays, nums1 and nums2 of length n and m respectively, and an integer k. You can choose exactly k pair of indices I1, j1, I2, j2, ik, jk such that all these i's are between 0 to n and all these j's are between 0 to m. For each chosen pair ij, you gain a score of nums at I into nums1 at I into nums2 at j. The total score is the sum of the product of all selected pairs. Return an integer representing the maximum achievable total score. Okay, so let's understand the problem using test cases. For example, here we are given two arrays 1, 3, 2. 4, 5, 1. For both of these arrays, we need to select k indices. All right, let's say we selected this and this index in nums1. Okay, we selected this and this index, so index 1 and 3, and this index, that is index 2 and 3. Now our score is equal to match the first element of selected indices from nums1 and nums2. So nums1 of 1 multiplied by nums2 of 2 plus nums1 of 3 multiplied by nums2 of 3. This is it. This is the total score. Now, over all such selections of indices, we want to maximize our score. All right, because in this particular selection, what is the score? It is equal to nums1 at 1, which is equal to 1, multiplied by nums2 at 2, which is equal to 5, plus nums1 at 3, which is equal to 2, multiplied by nums2 at 3, which is equal to 1. So total score is equal to 7. All right, but we can have a score 22. How? By choosing indices. Uh, this is zero based indexing. So 2 comma 0 and 3 comma 2. 2 comma 0. Another selection can be 2 3. How is 2 3 coming? This I, this I, this J, this J. So 2 3 1 2 1 2. All right. So this index is matched with this index, and this index is matched with this index. So what is the score? The score is equal to nums1 at 2 multiplied by nums2 at 1 plus nums1 at 3 multiplied by nums2 at 2. What is the total score now? Nums1 at 2, 3 multiplied by nums2 at 1, 4 plus 2 multiplied by 5. What is the total score? 12, that is 12 plus 20, which is equal to 12 plus 10, which is equal to 22. All right. This score is greater than this score. So over all such selections of indices, here one selection was 1 3 and 2 3. Here one selection is 2 3 and 1 2. There can be many such selections. All right. So over all such selections, we want to find out the maximum score. Now, observe one thing. Let's say we picked first pair of indices as I1 and J1. Okay, there were two arrays, nums1. Some elements were there, then I1, then some elements are there. Then nums2, some elements are there, J1, then some elements are there. All right. Now, if we analyze, now what more do we need to do? The score due to first pair is equal to nums at I1 multiplied by nums at J2. Now we need to select k minus 1 extra pairs. All right. Total number of selected pairs is equal to k. So one pair is selected. So we need to select more k minus 1 pairs. Isn't this same as our, what was initial aim? Select k pairs from nums1 and nums2. Let's say from range 1 to m in nums2 and from range 1 to n in nums1. Isn't this same as the score we got after selecting I1 and I2? Score 1 plus select k minus 1 pairs from nums1 I1 plus 1 till n and nums2 J1 plus 1 up till m. Alright. So isn't this a repeating problem? If we consider nums1 from I1 plus 1 up till n as a new array, then we are applying the same operation, that is same problem statement on this two new arrays. Alright. So isn't this overlapping problems? And what have we learned in the case of overlapping problems? In case of overlapping problems, dynamic programming DP is a possible contender. Okay. So try to find out what can be the possible states from state I comma j comma k. That is, let's say index 1 of our array. That is, what are the starting points? Here starting points were 1 and 1 and the number of elements to be selected were k. we reached to a state I1 plus 1, J1 plus 1. This I1 plus 1 represents a new subarray and J1 plus 1 represents a new subarray. The problem statement is same. Okay. Generally, we write down func to represent problem statement. The problem statement from index 1 in array 1, index 1 in array 2, and total number of selected elements is k, is same as problem statement of index I1 plus 1 in nums 1 and index j1 plus 1 in nums 2 and k minus 1 number of elements are to be selected. Okay. So, can we find any problem in this particular state? No, the state is very much correct, all right, because there are overlapping statements. So if we have got our state, how can we find our recurrence relation? First of all, let's analyze the time complexity of our current state and current constraints that are given to us. The value of n is up till 100. The value of m is up till 100. The value of k is minimum of n comma m, which can go up till 100. Okay, if this both are 100. So currently, for just building this state, we want 10 to the power 6 number of computations. All right, n into m into k. Okay, so for recurrence, we do not have any time complexity left. Okay, O of 10 you can say, which is very much constant time. Okay, equivalent to constant. So if for each I, j and k we iterate over all the remaining suffix array value, that is after this I and j we move to after this I1 and j1 we move to I2 and j2. If we find all such pairs, we would want extra n into m time complexity. All right, so this is a wrong recurrence. So how can we find a better recurrence? Okay, so instead of finding okay, first of all, uh, instead of finding the uh, maximum value in suffix of I1 to J1, we find the maximum. These are just optimizations. Our logic is very much clear now. How to optimize our recurrence relation so that it pass in this given constraint. Our new DP state is DP state maximum score from prefix I1 in nums and prefix I2 in nums 2. Prefix I1 in nums 1 and prefix I2 in nums 2. Or not I2, it's actually J1. Let's not name this as K. Let's name this as X, such that X pairs are selected. All right. If this is the case, what do we need to answer? We need to answer dp of n, m, k. Okay. N covers whole subarray or whole array nums 1. M covers whole array nums 2. And in these whole arrays, we want to pick up k uh, indices. And after picking k pair of indices, what is the maximum score we can obtain? that is dp at n into m, dp n m k. All right, this is to be returned. What is the base case in this scenario? If at any index I j, if number of pairs selected is 0, then score is 0. Okay, no score, no pair selected is equivalent to no score. Base case. Now, what is the recurrence in this scenario? For each index pair I comma j, v or I comma j comma x, we want the maximum value of I minus 1, j minus 1 and x minus 1. Okay, what do we want? In prefix up till index I of nums 1 and prefix up till index j of nums 2. If we want to pick x pairs, then this need to be updated uh, with maximum value of dp from index from prefix I minus 1, j minus 1 nums 2 and x minus 1. This must be complicated to understand. Okay, so let's say we want dp of I, j, x in this scenario. What do it represent? It represents maximum score for prefix I1 in nums 1, prefix j in nums 2, such that k pairs are selected. So for calculating this, we would write a loop like this, for int new I or previous I equals to I minus 1. It would go up till index 0, I minus minus. And similarly for prefix previous j, previous j is equal to j minus 1, previous j greater than equal to 0, previous j minus minus. Won't we? We would be writing our recurrence like this if we had the option to iterate over all possible previous pairs that was initially selected. dp of previous I, previous j, and how many pairs were selected initially, x minus 1, and if the current pair is selected, what is the score due to pair ing. Okay, if we want to collect uh, if we want to find dp at I, j, x such that the current index is also chosen as well. If it is not chosen, we would just update with the x value of the previous I and previous j's. Okay, so if anyhow we could find this score is constant. Okay, score of I and j do not depend upon previous I and previous j. This particular thing is constant. If anyhow we find the maximum value of uh, this particular dp value, that is previous I, previous j and x minus 1, this x minus 1 is fixed. All right, then for sure we can reduce these extra for loops. And can we find this the max value of this dp? Yes, with a prefix maximum. Okay, let's say what is this dpij? We want dp maximum value of dp previous I, previous j. If we do not consider this third index, okay, just previous I and previous j, this is a matrix for sure. Okay, let's build a matrix. Let's say this is the matrix. If we currently want the maximum, we want to calculate dpij, and let's say this is that ij, this 2 comma 2, or let's say this 3 comma 3 is that ij. Okay, this particular cell. Then we want the maximum value of dp previous I and previous j. How, what are previous I and previous j? I is smaller than this particular I, is this portion, and j is smaller than this particular j, that is this portion. So we want the maximum value from this grid. Okay, this is the new grid. We want the maximum value from this grid, such that this maximum value contributes and adds upon with this fixed score, which is a constant, and it gives us the value of dpij. All right. So how can we calculate the maximum value of uh, a particular grid? This can be done using prefix max function. Okay, if we just wanted to do it in 1D, all right, in a 1D array, just have a prefix max. How would it look like? If we want prefix max at index I, we would just say prefix max at index I is equal to maximum of prefix max up till index I minus 1 and the value at current index. But now we are considering a matrix. So if we want to calculate for this particular cell, we want to calculate the prefix for this particular cell. Where can this prefix come from? It can come from this particular cell. Okay. It can come from this particular cell, or it can be the element present at this particular cell itself. All right. So in 2D, this particular function changes like this. In 2D, it is prefix max of I, j is equal to max of all these elements, prefix max I minus 1, j, comma, prefix max I, j minus 1, I minus 1, j, comma, prefix max of I, j minus 1, comma, the current value num set ij. So if we have the prefix max for this particular portion, we can get rid of this particular loop and just uh, use this particular value, prefix max value, add it with the score, and the maximum dp value which we can get is calculated in O of 1. Okay, using prefix max on matrix, this function or this loop is reduced to O of 1. All right. So this is it. The rest, the base case is clear. The recurrence is very much clear. Now we just need to implement this thing. So let's move to the implementation part. Okay, one more thing. Here I initially submitted some solutions and got MLE because I was using a 3D vector. So I just reduced the memory limit by converting it into two sized vector instead of k sized vector here. But after discussion with some of my friends, I came to know that this would get accepted if I just convert this vector into a DP. So you can remember this thing for future purposes, as I will as well. So here, this DP represents our current DP table that we want to build, and this DP1 represents the prefix sum. So I did not wanted to name it as prefix sum, so I just named it as DP1. Okay, so we initially just understand the memory limit exceeded code first. Here we are building a DP table of n plus 1, m plus 1 and k plus 1. Similarly, DP1, which is a prefix sum initially. Now, what is the base case? For any x is equal to 0, for any indexes, if x is equal to 0, the DP value is equal to 0. And what is the prefix sum? Prefix max? Prefix max is equal to 0 as well. Now, start iterating from k is equal to 1 or x is equal to 1 up till x is equal to k. All right. Because for a particular index x, we want the prefix max of uh, choice x minus 1. All right. So iterate or fill the DP table for a particular x, build a prefix sum using that particular x or prefix max using that particular x, and use that prefix max to initialize the answer for x plus 1. Okay, that is it. So that is why we are iterating over x first, then iterate over all the possible I and j. Now DP at ijx is equal to what is the maximum max we have gotten so far, that is prefix max, plus uh, nums1 at I minus 1 multiplied by nums2 at j minus 1. Why this minus 1? Because we are considering 1 based indexing, but input is given in 0 based indexing. So I minus 1 and j minus 1. That is it. So this DP gives us number of indices, number of pairs, number of ways to choose k pairs such that the last choice is pair I and j. Okay. And DP1 represents the prefix sum up till prefix max up till pair ij. All right. Now at the end, the end choice can be any possible indices, pair of indices I and j. Okay. So for that sake, iterate over whole DP table and find the maximum value present in that DP table such that k pairs are chosen at the end, and that particular choice will be returned as our answer. This gave memory limit exceeded because just because I was creating a vector of 1e6 which is not allowed locally. Instead, I thought of reducing the space complexity by creating a two-sized k dimension. Okay, now every time if we want to process, just initialize it with minus infinity, the current x, and the current x is represented by x modulo 2 and the previous x is represented by 1 minus x modulo 2. So if the current k is odd, so the one part of dp will be, that is one dimension 1 will be updated using dimension 0, and if dimension 0 is used, dimension 0 will be updated. Even portion is used, dimension 0 will be updated using dimension 1. That is it. So this was it for the last problem as well. uh, thank you for joining. I hope you give your best in upcoming contest. We will be discussing the next code forces contest as well in the same channel. Stay tuned for the discussion. Thank you for joining.